got the sample assessment material. So this is the paper they released before any official exams. This is for Year 11 triple higher tier. Equation sheet. And in with the first question. A little bit of numeracy to start off with. A little bit of blurb. You've got some data in a table. The first question is, what is the total time that Usain Bolt improved on Powell's world record? So you can see where I've got it from. The table, the yellow and the green, and I've taken one from the other to give me 0.16 seconds. Use the equation now to calculate Bolt's mean time. So I've used the distance of 100 meters, and I've used his best time there, 9.58. With his final record time anyway, that's why I've done that one. That comes out to be 10.44, and then the unit is meters per second for 3 marks. Why do top sprinters need to be physically strong? Because they need strong muscle legs to exert a large force. Bit of a nonsense question if you ask me, but it was in there. When a gun is fired at the start of the race, suggests why top sprinters try to exert their backwards force. It's to get that maximum forward force to get a larger acceleration there. And then we've got to complete this graph. So initially he's going to be accelerating, but he's going to start not slowing down, but the acceleration is going to get less. So until he gets to terminal speed there, and then when he stops, It's dramatic decrease. So that's going to be a big drop, and then tails off there. Question 2. Question 2 is all about a cricket player. Explain the motion of the cricket ball as it hits, as it is high into the air by the batsman. So we're just talking about vertical motion here. I'm going to say as it goes up, okay, it's going to start to slow down. We call it decelerate. So it's going to start to slow down until it stops, comes to a stop, and then it's going to fall back down. So it's going to accelerate as it falls because gravity is pulling down on it. That's what's happening there. Calculate the change of momentum of the ball. So this is applying to triple only. So you can see I've got the mass and the speed there. So that's momentum. Momentum change 6.4. Use equation for page 2, which is force and change of momentum over time. So I got that 6.4, which is my change of momentum over the time of 0.4 seconds. Give me 16 newtons. If the cricketer halves the time taken to stop the ball, the force is going to increase, isn't it? Because you're halving the time, and you could increase the time. You could decrease the time yourself to see, but I guarantee it's going to increase the force. So for 1 mark, I didn't show my workings out. I just told them it increases. What advice would you give? Well, if you bend your knees on landing, and this kind of relates to, they often wrap this up in a car safety question where they say, what does a seatbelt or an airbag or a crumple zone do? Well, because he's bending his knees on landing, he's going to increase the time or the distance to stop, therefore decreasing the force on the legs. So if it was a car question, you would say it's going to increase the time or the distance for the passenger or the driver to hit their head on the dash, therefore decreasing the force. And there's a way you can prove that, but I'm not doing it here. Question 3 then, you've got the pivot and moment question. We've got a bunch of data. And this is shaded out on purpose because this is what we would need to be plotting on the table graph over, I should say. It's worth 3 marks. So I've got a scale going up. I've got my plotting with a mark, and then I've got my line or my curve. And again, it needs to be nice, straight, confident line. Describe the trend. So as distance increases, the weight decreases at a decreasing rate. So it's coming down at a decreasing rate. Oops. And one student in the group states that when weight was 1.5, the force, change the force by 0.5 would change the distance by... So if you pick 1.5, start at 1.5, and then change it by 0.5 every time, then that's going to change the distance by 5 centimeters. Is this true? Well, let's have a look. So 1.5 equals 20 from the graph. 2 equals 16 from the graph. So you can already see it's not increasing by 5 there. So that's a 6. And then 2.5 is 11 centimeters. That can't be right. Yeah, it can, because it's coming down. So that's the difference. There is 4 centimeters. The difference there is 5 centimeters. So the claim is true there, but the claim is not true, because you can see that it's not happening there. And then we've got conservation question here, where the moment on this side has got to equal the moment on that side. So I'm taking 10 newtons, and I'm not converting this to meters because it's all in centimeters. So it'll all come out in the wash. So 10 times 20 plus 4 times 10 is going to equal 40F. So when I multiply and when I simplify that, we come out to 6 newtons. One more question, then 2 more pages, and then I'll do another video then to keep these videos quite short. So the space question, I've highlighted Saturn for a reason, because that's what's going to come up in the question. Use the data in a table and a graph to answer the following question. What is the orbit speed of Saturn? So first of all, because this is a graph showing mean distance against speed, I need to get Saturn's mean distance, which is 14 from there. Okay. And then when I put that on the graph, which is there, because each square is worth 0.5, I come out with 3 times 10 to the power 8. Why is it times 10 to the power 8? Because it's there. Okay? And then last page, dwarf planet, 700 kilometers in diameter. That's there trying to throw you off. As an orbital speed of, we need this, and it travels this distance. We need that. Using a graph, find the distance. So now it's kind of a backwards way to do it, but we got to look at the distance there. Let's look at the speed, 5.8. So we're going to look at 5.8, which is there, and then that comes down to be 4.5. Remember, 1, 2, 3, 4, 4.5. Each square is 0.5 there. And now we can use what's in the question to calculate the orbit time. So that's distance. Distance is there, kilometers, and then your speed is there, kilometers per year. Okay, so I put one over the other, and I come out to 4.6 years. No conversions required, because that's years, and that's years, and kilometers. Estimate the mean temperature. So that is looking at the graph now. I'm going to see where that. So I've got 4.6 years orbit time. Is that what I used? Yeah. Orbit time 4.6. You can stick within there. Or you can actually use the mean distance. I think actually I used the mean distance, because the mean distance was between Mars and Jupiter. So it's going to be a range between minus 23 and minus 150. So I've said there, just to be safe, minus 45 and minus 100. That's any number between there, you're going to be safe. The reason must fall between Mars and Jupiter. Two reasons why this takes longer than Earth to complete one orbit. Well, first of all, it's got a bigger distance to travel than Earth, because it's just past Mars, and its speed is less than Earth. So that is part 1. Thanks for watching, and make sure you watch questions 5 to 8 now on part 2.